Well, it looks like we can start. I'm glad you made it in, Max. For the others that will watch this video later on YouTube, or welcome back to those as well. Well, for what we have going on today, the biggest announcement is that our third exam is going to be next Tuesday. Before we go into the announcements, any questions at all to start us out today, Max?
I'm good, thanks.
You bet. It's kind of weird being the only person in class, so don't hesitate to chime in at any point. One thing I should mention is I was not quite prepared for how low attendance would be in this class. It's kind of a strange feeling for me as well. I think a lot of people are doing just fine watching the videos later on in YouTube, so we'll still just make the most of it. Well, for what's going on in exam three, I decided not to stretch it into a really, really long exam. So I ended it here on the section 8.6. This is solving square root equations, and that's what the quiz number 10 is based on. So the sooner you can get that completed and sent in to me, I'll try to get that graded and sent back as soon as possible. And you'll have a good idea of how you're doing in that section 8.6. 7.1, 7.4, 7.5 are all, and 7.6 are dealing with rational equations and inequalities. And then the chapter 8 is all about square roots. 8.6 is square root equations. To get a good feel for what the real exam questions are going to look like, since we don't have a big review for these classes, I try to give an extensive set of the sample exams. So I'm not going to ask anything too different based on what you did in the homework, what we did in class, and on the quizzes. And these two versions of the sample exams are kind of the same types of problems we've seen on the exam one reviews, exam two reviews as well. And on the Newton homework system, you can find a practice exam in that system as well if you'd like to give it a try. So if any questions come up while you're studying on this over the weekend, don't hesitate to reach out. I'll be available and happy to help. Just to keep on schedule so we're not too far behind at the end of the class, we will do a review before the final exam. But we have to push forward into the new material, section 9.5, and see how far we get in section 9.6. So that's where we're at so far. Any last questions at all before we jump in? Okay, well, we did most of the problems, it turns out, in section 9.5. We skipped around a little bit towards the end on Tuesday's class just to do a smaller one. And so we're going to go back to the third example and the fifth example. Here's where we left off, or here's the problem we skipped over last class on Tuesday. This problem is pretty similar to what's going on in section 7.5, applications to rational functions. In fact, this one turns into a rational function. And so in a real sense, this is a pretty decent review problem in its own right. It's talking about interesting fellow Roy, who kayaks up the river and then back in a total time of 6 hours. But the moment you spot information that looks like this, the immediate red flag that should go off in the back of our mind is this is a distance equals rate times time problem. So that's the formula that we're going to throw down. We saw in section 7.5 on the rational equations that you could also re-express this whole thing as time equals distance divided by rate. And this is the way we're actually going to use the formula in this problem. So Roy kayaked up the river and then back in a total time of 6 hours. That means there's two different kinds of rates, the rate of speed when he was going up the river and when he was going back down the river. So we can also organize a problem by saying, here is the situation for when Roy was going up the river. And I'll interpret up the river to mean against the current. Then back, so I'll say down the river when he's going back. Interpret that to mean going with the current. So we'll set up two different kinds of equations based off this formula for the different kinds of rate of speeds up the river versus down the river. We're told that the trip was 4 miles each way, so that's pretty helpful. So distance equals 4 miles. And 4 miles on both. MI for miles. We're told the current was difficult. I'm not sure what to do with that information, but it sounds like Roy kayaks at a rate of speed of 5 miles per hour. The current was probably pretty close to that amount. Looks like that's kind of a hint that's being given in the problem. So this information is going to be tied in with the variable R, rate of speed. So it's something that we'll incorporate here and here. Let's write out Roy's rate of speed is equal to 5 miles per hour. The second part of the problem now says, or the sentence, what is the speed of the current? So that's the unknown. We can give this a variable name, say, how about C for speed of the current? C equals the speed of the current. Actually, let me change up the color coding here because these are both going to be used in the rate R. I think it makes sense to keep both of these blue actually. So C equals speed of the current. So we can use this piece of information to write down the rates in both scenarios. On this one, when we're going against the current, first it's going to be Roy's speed, 5 miles per hour. Then it's going to involve the speed of the current. But for going against the current, here's where we would put in a minus. So Roy's speed has been severely reduced a lot by the sound of it. The current was difficult, the problem tells us kind of cryptically. Then we do it all over again here. Rate of speed is going to be Roy's speed first. We're going with the current, so that means the speeds are going to add up this time. So go plus the speed of the current. So the return trip back down, even though it was 4 miles, it was probably a lot quicker, probably close to twice as fast. So with both of these, we can write out the equation now for time. We just put it together in this way. We might as well use green for distance. The trip was 4 miles each way. So in both these expressions we write out, time is going to be equal to 4 in the numerator both times, but the denominators change. We have 5 minus c on this expression. Time equals 4 divided by 5 plus c on this one. So now that everything was separated out, we now have 2 different amounts of times. The units on these are going to be in hours. The rates are in miles per hour, and the distances were in miles. And after setting up all of this, we don't yet have an equation, but there's still one piece of information we haven't used. It was this right here. The total time that Roy's been on the water kayaking, hopefully having a good time, not in distress, was 6 hours. So if we take the time going against the current, the time going with the current, that's just going to balance to the total time of 6 hours. So writing this out, we have 4 divided by 5 minus c plus 4 divided by 5 plus c equals 6 hours. So adding up all the times, and we get the total time on the far right. That gives us finally a nice equation to solve. And again, this is a pretty similar equation that you might have seen in section 7.5. Next, we're just going to solve this as if it was a chapter 7 question. The next thing we would look for are the excluded values. Let's use maybe a different color at this point. The excluded values are the parts that make the denominator go to 0. One excluded value from this denominator is when c equals 5. So we'll say that can't happen. C is not equal to 5. And likewise from over here, c cannot be equal to -5. And they make sense in this problem because, well, first, c is a rate of speed of the current. It can't be negative. That's a positive quantity. And if c was 5 miles per hour, that's exactly Roy's rate of speed. It would mean Roy never covered any distance. He would be looking, from our point of view, like he's still in the water as he's rowing at 5 miles per hour. And the current is also flowing at 5 miles per hour. He's not getting any distance. So he would never have done the 4 miles. So these are sensible things that just didn't even make sense in the problem whatsoever. Once we have those two things, the next thing we do is grab the least common denominator, which is 5 minus c times 5 plus c. We'll multiply it into both sides of the equation to clear off these two denominators. So let's scroll a little bit to get through to the algebra part. Take 4 times 5 minus c, 5 plus c, write it over the old denominator, 5 minus c. Then just keep on doing it all over again. Here's 4 times the least common denominator again. Divide by 5 plus c. And the right-hand side doesn't have a denominator. It still multiplies by 5 minus c times 5 plus c. So the equation gets messier at this stage, but now we have some simplifications. The major thing that made this equation a little bit harder is the denominator. But at this point, when we do the cancellations, those denominators are gone. So on the left, it's just 4 times 5 plus c plus 4 times, here the survivor is 5 minus c, equals, nothing canceled off here, but that's a difference of square setup. So this becomes 6 times 5 times 5 for 25. When you multiply here to here, that's 5c. Here to here is negative 5c, so middle terms cancel. So it's just 25 minus c squared. So that simplifies nicely as the difference of squares. This is the factorization for factoring 25 minus c squared. Now we can just start solving this as it stands. We get distributing 20 plus 4c plus 20 minus 4c equals 6 by 25, giving us 150 minus 6c squared. It's now a quadratic equation, so it makes sense that this is section 9.5 application of quadratics, but not every problem has the worst equation. This one's actually not too bad because one nice thing really happens. The degree 1 term just vanishes. And now we're left with 40 equals 150 minus 6c squared. So now the method to solve this one is not the quadratic formula. This is kind of the odd one out in the whole set of notes. Here, we'll just use the square root method. So use the square root method, all because the degree 1 term cancels off. So all we need to do is solve for the c squared part, subtract 150 from both sides. Negative 110 is negative 6c squared. Divide by negative 6. And 110 sixths equals c squared. Here's the point where the problem can be pretty dangerous as an exam question. As an ordinary equation like this, there are 2 solutions. Square root method means square root this side, square root this side, and you get 2 possibilities, plus or minus. But when we solve for c, it's a rate of speed. C has to be positive. So in just this problem, we'll ignore the negative sign right here and only take the positive of square root 110 divided by 6. But if this wasn't a word problem, if this was just a generic equation, we have to give both of those solutions. And we're about there. The problem said, let's see here, round to the nearest tenth. So once we get to this stage, we're just throwing it into the calculator. So in the calculator, you're just using the positive root. We have 110 divided by 6. And to the nearest tenth, that would be 4.3 miles per hour. So the speed of the current comes out as 4.3 miles per hour. And it makes sense when they said the current was tough, because Roy is kayaking at 5 miles per hour. That means when he's going against the river, he's doing just 0.7 miles an hour, trying to cover all that ground. That makes sense. He was on the water for 6 whole hours. That would have been excruciating. But that's the conclusion on this one. Most of the problems in this section do involve the quadratic formula, but the moment something like this happens, C gets eliminated, it's a faster solution. Well, any questions getting through this one? Okay, well, we have one more to take a look into. The next one will involve the quadratic formula, so that'll be a good review on that. Below is the one that we skipped across, but we'll come back to this one before we go into the next section, section 9.6, graphing quadratic functions. In fact, when we looked at this problem and thought about it, we threw in a really rough sketch of the graph. So we're going to be doing more of this in the very next section. This one comes up as a homework problem. It could potentially be a final exam problem as well, but it's one of the nicer problems ever because there's not a lot of setup. They give us from physics a function h for height as negative 16 squared times v naught, which is just your initial rate of speed or initial velocity, times t. They gave us an initial height that we're looking into, 400 feet, so that plugged in for height. The rate of speed was 220 feet per second, so we just plugged that in for v naught, the initial velocity. And then this became a quadratic equation. We subtract 400 from both sides, and it looks like this to start out. Negative 16t squared plus 220t minus 400. And that's not too bad to shove into the quadratic formula. The numbers get a little bit large and slightly tedious, but that's why we divide by negative 16 and turn into this. T squared minus 13.75 plus 25, 13.75t times t rather, plus 25. And this is just a little bit nicer to put into the quadratic formula, making the numbers more manageable. These were the A, B, C coefficients. We did this in chunks, doing the discriminant first, b squared minus 4ac. Then we put it all together, threw it into the calculator, and found two different times it qualifies. The height of this arrow shot up into the sky reaches 400 feet twice, once at 2.16 seconds. That's at the initial takeoff. Then it reaches some maximum height. We'll need the next sections to find out what is that maximum height if we're curious. And then as it's falling down, 11.59 seconds later, this is where it hits a height of 400 again. But really the big takeaway of example 4 is the graphs of some of these things are sometimes pretty interesting. And so we'll be looking into those graphs with the main idea of sometimes the major question we want to ask is, how high did this arrow go? What was its maximum height? And still other problems, we'd want to know what is the minimum height. And so we'll develop techniques for graphing these parabolas and looking for these maximum and minimal values, which we'll later call the location of the vertex of the parabola. But again, it was just another quick way to put down a quadratic formula and practice with it. So here's the last problem for these sections notes. This one's a little bit tricky because it goes back to chapter 7 for a rate of work style question. So back to that chapter 7, let's review that just to get a warm up on how we're going to solve this one. This was a section 7.5 problem. And there were two interesting problems at the very bottom of these notes after the uniform motion problems. Let's go to the very bottom. And they are the rate of work type problems. The idea with rates, whether they're rates of a current in a rake of Roy kayaking, or the rate of work, the time it takes for a person to do one job per A units of time, the key idea about rates is they add up. So if A is the time it takes one person to do a certain job, B is the time to take another person to do that same job, this is just saying one job per, say, 60 minutes, A units of time. One job per maybe 70 minutes, B units of time. And we can add up those rates, and that would be the total rate of speed it takes if they are both working together to do one job. So this is the major idea from the last example. This is something we can expect as a problem as well on the upcoming exam 3. So let's put this on the notes, work through this really carefully, just as a reminder and kind of a review question as well for the upcoming exam. The only thing that's not on the exam is the quadratic formula stuff. So when we go to use the quadratic formula, the equation will be easier as the real exam question is the thing to remember. Okay, so there's our big idea for this one. And how do we know it's probably a rate of work problem? Well, it says two gardeners can do the weekly yard maintenance in 29 minutes if they work together. That's just talking about the C value, the time it takes to finish a job, weekly yard maintenance, when both people or both things are working together. This is people this time. So this line alone tells us it's a rate of work type of a problem. And they gave us the C value. So we'll say, just to start this off, C, which is equal to the time if the gardeners work together, equals the 29 minutes. So that's handy. That gets us started. We have one part of the equation, the right-hand side, already set up. Then there's two other people in this problem. There's an older gardener that takes 12 minutes more than the younger gardener to finish the job by himself. So it says next, how long does it take for each gardener to do the weekly yard maintenance if they worked individually? Someone called him sick, maybe. So this could be, say, maybe the grounds person for ISU. Could be a pretty serious job. There's a older one that takes 12 minutes longer than the younger one. So let's write down both of those unknown quantities. I'll go with, say, an X and a Y on this one. I don't actually want to use B because B is part of the quadratic formula, and that could be really confusing. So I'll just go with X and Y for this generically. So start off with X. X is going to be the time it takes the older gardener to complete the job. And finally, Y equals time it takes the younger gardener to complete the job. And the job is doing the weekly yard maintenance, whatever that is, probably mowing, trimming, that kind of stuff. So if we put all these together, the X, the Y, and the total time together, the rate of work equation tells us that 1 over X, the rate of speed to do the weekly yard maintenance for the younger gardener, plus the rate of speed for the older gardener to do the one job, 1 over Y, is the total speed. It takes them as a total rate, 1 over 29. This means do one job of the weekly yard maintenance per 29 minutes. This is if they're both working together, assuming that they get along perfectly, they never bump into each other, they're just perfectly synchronized when they're working together. So this is our setup so far. The problem says, how long does it take for each gardener to do the weekly yard maintenance working individually? So we need to solve for X and Y in this problem. And that's pretty tough because there's two variables in one equation, but there's one sentence, one bit of information we haven't used yet. The older gardener, so that's going to be the green one, takes 12 minutes more than the younger gardener to finish the job by himself. If we use that sentence, we can find a relationship between X and Y and make a substitution right here. That's going to allow us to solve the whole problem and get the values out. So this is what the setup looks like. And really to this point on, this is very similar to what an exam 3 question could look like in chapter 7. Again, the only difference is the final equation solving phase where we'll use the quadratic formula in this section to solve it. Well, let's take another look at this equation. When it says the older gardener, that's going to be the variable X. It takes this person 12 minutes more, so that's going to be plus 12, than the younger gardener to finish the job by himself. So when it referred to the younger gardener, that was the variable Y that we put down. So it gives us this equation. The time it takes the older gardener is 12 minutes longer than the time it takes for the younger gardener to do that job. And it's not age discrimination. Maybe the older gardener potentially, for example, is just more thorough. So it's not necessarily saying the younger gardener works faster necessarily. But once we put all this together, we have y plus 12 in that denominator. So here's our next substitution. 1 over y plus 12 plus 1 over y equals 1 over 29. Now it's one equation with one variable. We can solve this for y. Once we have the y value, we'll just substitute that back here and get the x value out. So this is where we do the next steps, solving the rational equation. We would often always go in this process, look into the excluded values. Let's work that out carefully. Again, just as a thought of this alone, if you study it as an equation just on its own, this is a section 7.4 review problem at this point. And this was the first thing we looked at. There's often extraneous solutions, just like in the square root section 8.6. So that's what we're trying to detect here before we get started. Excluded value would happen right here if y was negative 12. So we say right away, y equals negative, cannot equal negative 12, which makes sense. It's a time. So if y was negative 12, it seems like we're implying time travel happened with the younger gardener somehow. And y also cannot be 0, which makes sense because if y were 0, then it's like the younger gardener just looked at the weekly yard maintenance and instantly did it in his mind, but being he's a wizard or something. So that's impossible. We put non-zero as well. So after the excluded values, like in most word problems or things that just seem silly, we wouldn't end a problem with either two of those values. But in a generic math problem, if there was no context, negatives or zeros could have been solutions, just not in this case because they make the denominators go to 0. By the way, that's one whole question really on exam 3. You'll have some problems where it just says, here's a random rational function. What are its excluded values? All you do is look for how the denominator could go to 0, and that solves the whole problem. Well, beyond that, we're going to use the least common denominator to clear out all three denominators in one shot. Least common denominator is something that all three denominators will divide into evenly. So we need a 29 to start it out. We'll need a factor of just y and another factor of y plus 12. So just like on the first problem we did for the day, we multiply all the numerators by this new quantity. We'll simplify by eliminating all denominators in just one shot. So let me rewrite the equation as 29y, y plus 12. It's multiplying the 1, so I just wrote it in as this. It's divided by y plus 12 plus 1 times that quantity again. So we can drop the 1 and just put in 29 y plus 12 divided by y equals 29. And then once again, least common denominator up top, 29. There we go. Y plus 12. So this is the messy side of the equation solving. Here, it cleans up because now we have a guaranteed, if we had the right least common denominator, of these kinds of cancellations. So on the second fraction, just y cancels, but you know that's still a big help. And this one, 29 cancels, leaving behind y plus 12. So now we have a quadratic equation. On this term, it's just 29y surviving, plus, on this term, it's 29 times y plus 12, equals, and on the last one, distribute to y through, and you get y squared plus 12y. Now it's a quadratic equation, and this would be a really tough one potentially to solve. In fact, it might have been one that was just totally inappropriate if it was in section 7.6, because we're told to round this one to the nearest tenth of a minute. That's a good giveaway that probably like in the last problem that we looked into, you're going to need your calculator and because y doesn't cancel here, we're going to need to use a quadratic formula. So to get the quadratic formula, we need 0 on one side. And even still, that's the same thing you would do for a section 7.5. Sorry, I think I said 7.6. 7.5 problem, the one that could be on an exam. So let's first distribute 29 here and start simplifying. 29y plus 29y plus large number. Here's the standard reminder of, don't forget to bring your calculator to exam 3. It's for situations like this. 29 times 12 comes out as a 348. And it's equal to y squared plus 12y. So now we can add the 29y's together. 29y plus 29y is 58y plus 348 equals y squared plus 12y. Then let's do some subtraction. Let's subtract 58y from both sides. Subtract 348 from both sides. One giant tally bar to say, do those operations column-wise. We get 0 plus 0, so just 0 on the left. And on the right, it's now y squared minus 46y minus 348. So that's our quadratic equation to solve. As an exam question, this one's going to be something that you could factor pretty readily. This one does not factor in a nice way, so this is the point at which it becomes different than the exam 3 question. But you know, even on the exam 3 question, if you wanted to, you can use a quadratic formula. You can't get hurt for knowing things, and if it's the right solution, you get the right solution. It's just probably going to be faster in the exam setting to factor the equation you get rather than use a quadratic formula. But for us, we need that formula, so that's what the next steps are all about. First, any questions at all, folks, getting to this stage of the problem? Okay, let's move forward to the next portion using the quadratic formula. So with the quadratic formula, we can say immediately that the solutions to this quadratic equation are going to be variable y equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So essentially, we're going to solve this just like we solved all the others in section 9.3 on the quadratic formula. We identify coefficients. The leading coefficient a is a 1 because this is really a 1 times y squared. Coefficient b is negative 46, making this problem tricky because of double negation right here. And the c coefficient is negative 348. So those are the 3 coefficients found. We're going to substitute in those values for a, b, and c here. But the next big thing that we calculated when we did the quadratic formula was the discriminant. So let's do that right here just to get it out of the way. B squared minus 4 times a times c, and this problem becomes, feeding the information from what you see above, b is negative 46 squared, minus 4 times 1 for an a times negative 348 for a c. And that's a big computation, but we can just jam it into the calculator. In the calculator, this becomes negative 46 squared minus 4 times 1 times negative 348. And we get 3,508 out of all that. 3,508. Running short on space, so let's take the strategy of alerting everyone if you come back to these notes. It continues. So y is now equal to negative of, first, in place of where b was, we're plugging in negative 46. So there's the double negation that we see here that was being mentioned. That's honestly one of the easiest things to miss about this. Sometimes when you see the negative b, it feels natural to put in a negative 46, not negative of negative 46. So watch out for that easy error to make there. Then it'll go plus or minus square root of b squared minus 4ac. but we computed that already to get 3,508. And 2 times A here is just a 2 times a 1, so nothing special. So what you would probably put in your calculator is something that would look like this. This cancels to a positive 46, plus or minus the square root, 3,508, divided by 2. I wrote the fraction in a funny way, just in line, so just as one line, as rather a stacked fraction like this. If you write it this way, by order of operations, you really need those parentheses. And that's important because that's how we would throw it into a calculator. So in a calculator, be sure to use the one that you would take to an exam setting, particularly, say, the final exam where this problem could come up. Here's what it would look like. I like this version of the calculator because you can put it all in one line, this entire thing that you see right here. So typing this in the calculator would look a bit like this. Start with a parenthesis. You can use a parenthesis symbol right here by the red dot, if it would hold still. There we go. Let me try again. There we go. It's a little finicky. It just doesn't want to listen to me. It looks like I'll use a different strategy here. Let's just box it out. So you want to use those parentheses symbols to write in your parentheses. So here's my first parenthesis, then type in 46. I'll do the minus version first. We can't put in a plus and minus on this calculator. Square root 3,508. And then you have to close the parenthesis right there. Then hit the division key from this spot here. We'll put in a slash. Now you're dividing by 2. Then just hit the enter key below and it'll spit out a number. This is a dummy calculator, so let me do it on one that actually works. Desmos is not a good one to use for the class because you can't take Desmos into an exam setting. So again, Desmos is really just for a classroom demonstration calculator, just a fast one for us to use. If I was doing this one, say at home to practice for an exam, I'd be doing it definitely on a calculator like this. But for the classroom demonstration, here's what we would get. 46 minus square root 3,508 divide by 2. We get a negative quantity, negative 6.61, rounding to 2 decimal places. Let's record the result. Y equals negative 6 point, and I already forgot, let me recall it again, 61. But we know that result's impossible because Y was the time it took the younger gardener to complete the weekly yard maintenance, I think it was. And so that couldn't be a negative time. That means the next thing we have to do is switch the operation to positive here and see what value we get. Cool trick on this calculator is you can use the up arrow to call in the last line that you put in, and then the left arrow to just move over and change it to a plus to save a lot of time. And same thing here, we'll just move over here, put in a plus, and it's 52.61 minutes. So there's our second solution. And this is about what your calculator would look like before hitting the enter key. Let me take a quick screenshot of that. Doesn't hurt to just leave it in the notes. Maybe not that gigantic though. Okay, so now that we have the two values, we have to remind ourselves this was a long math problem. It's easy to forget it was more than just a fun math problem like doing this one. Y had a meaning. It was the time it took the younger gardener to complete the job. We found Y equals 52.61 minutes. We eliminate this because time had to be positive. So let's go back to saying Y equals 52.61 minutes. We already said that Y equals the time it takes the gardener, the younger gardener, to do the job. So you wouldn't have to reiterate that if you've already said it once. We also needed the other time, the time for the older gardener. So take 52.61, plug it right here. We're just adding 12, which makes sense. Takes 12 minutes more for the older gardener. So take this answer add 12 to it, and you'd get 64.61. We're rounding to the nearest hundredth, but that's okay. If you gave me a little bit more accuracy in exam setting, that wouldn't hurt at all. So let's leave it with the extra approximation just to convey that's fine. So 52.61, add 12 minutes is another way to visualize it. You get 64.61 minutes. So those are the times we were looking for. Kind of a long adventure of a problem since it seemed to cover a lot of ground, lots of different things we reviewed to get to that point. But we did it, folks. This is the coverage for the applications to the quadratic equations. Any last questions at all before we close out the notes on this one? Okay, and again, just as a reminder, we'll solve equations like these on exam 3, and some of them come from word problems like this one, using this idea. And the same idea up to this point is pretty similar to what you would do in a real exam problem, except this one was nasty. This one went to beyond, we need the quadratic formula. That part won't happen on the exam question. Expect that your equation to be a lot easier to solve once you get to this stage. Other big takeaway with these notes, like we mentioned before, is we want to return to this concept. The fact that if you have a quadratic equation, say this format where we cleared the values, making them simpler, t squared plus or minus some constant times t, plus or minus some additional constant, gives you shapes that look like this. And that's what we're going to explore in the very next section. It's useful to us because we want to know the maximum values and minimal values as a whole new slew of applications that we can be getting into. So let's take a look into next, section 9.6. Let me close out some of these windows so the computer doesn't work too hard. Looks like this is a section that we probably won't finish today. That would be really rushing through it and racing through it. So this is one that we'll come back to when we're 1 week away from today. We won't hold class next Tuesday since we reserved that time for the exam. So on this problem right here, that's a nice warm-up problem of just graphing the line. Then we're going to start graphing things like the quadratics, like y equals x squared, using new ideas like vertex form, vertex axis of symmetry, whether the graph opens upwards or downwards. That's a lot of information to put together, and the vertex form of the quadratic right here is kind of the nice key when it comes to graphing any one of these. And we saw a similar sort of idea when it came to graphing the line in this warm-up problem. You could graph this line by finding intercepts. It's a pretty decent way to do it. But if the line started off in a specific kind of form, kind of like a vertex form, say, graphing the line would be really pretty immediate. So let's first put it in that form. We get that nice form for graphing the lines when you solve for the y variable. This y variable solved, but also a square has been completed to get it into vertex form. So to solve this one, first subtract 2x. 5y is negative 2x plus 10, then divide by 5. Y equals negative 2/5, x plus 2. But now that we got to this stage, this is the so-called slope, intercept, form. This was really handy because if you have a y-intercept and you have a slope, that's probably the easiest way to graph the line, just using those two pieces of information. So slope-intercept form for these kind of equations is analogous to vertex form for quadratic equations or quadratic functions. The only thing that makes it quadratic is the power 2 or the degree 2 that occurs, giving us an x squared in the problem, much like the x squared down below here on this other warm-up problem. We might as well finish this one off now that we're looking at it. The slope is m, negative 2/5. The y-intercept is found by plugging in 0 in for x. That was supposed to be a 0. Let me try again. But notice when you put it in as 0 for x, this whole first term is gone, and you just get a positive 2. So that 2 that you're looking at there is automatically the y-intercept. Then the graph of this line goes like this. First plot the y-intercept. It's on the y-axis at height 0, 2. Then the slope is just a set of instructions like on a map to get to the next point. The numerator of -2 says go down 2. Denominator 5 says go right 5. And that's automatically our next point. Then this would be the quick graph for the equation, 2x plus 5y equals 10. So we did it, folks. This is our warm-up problem. What we're doing is just building off of this, using special forms to plot lines and special key information to plot higher degree equations, things that aren't linear any longer, the quadratic forms. And notice what happens when you put something like this into a graph. First, let's put it in as a degree 1 linear equation. It's y equals -2/5 x plus 2. But the moment you change x and bump the degree by power 2, you get this. The whole shape bends, and this is what we mean by a parabola or a quadratic function. Just trying to find a good place to park this. There we go. Interesting things about this particular graph right here is it's not in vertex form exactly, but we can make it look like vertex form. The vertex form for this would be, forget that doesn't stay put if I click there. The vertex form is this. Y equals -2/5, go x minus 0 and then square it. That reveals what's in the middle. That value here corresponds to that value h. And that's correct because x minus 0 just simplifies to x. That would be squared, going back to the original thing. And then plus 2. So that's what it would look like actually in a vertex form. I mean, it kind of was here, but this is more very literally showing what the h is and then the k as well. So it matches up the form in a more stronger sense. It tells us the vertex is always located at coordinates hk. So that tells us for our problem, what are the coordinates? We'll often just say v for vertex. And notice how we get these coordinates. There was a negative h here, so it goes down to a positive h. Here, no big difference. -0 goes down to a positive 0, so it's going to be 0. And then this k right here becomes a second coordinate of the vertex. The k is taking the role of 2 on our problem, so a 2 would go here. Here's the 2. But if you plot 0, 2, that's just this spot right here. This is the vertex. It's the highest point on our parabola. The reason it's the highest point is because of what statements 3 and 4 are saying. A is the leading coefficient, the thing that goes in front. Our a value is a -2/5. Because it's negative, it tells us the parabola opens downward. And that's why it has this shape. Opening downward means it has a maximum value. And this is the open downwards part here and here. So that negative is panning out on this part right here. Just looking for a color that's going to make sense. The fact that this part is negative means opens downward. I'll just say down for lack of space. Well, it had a y-intercept at 0, 2, x-intercept at that nasty value and that other nasty value. Vertex was the highest point on the graph. And so that's what this vertex form is trying to tell us. We'll practice this more on actual concrete examples for the next ones and build out our own graphs by hand from scratch. But just to think about what this is all thinking, here's our second warm-up problem. Coming from this quick graph right here. Sorry, just trying to get that spaced out a little bit better. Let's copy this down so we can start off clean and fresh right above example 1. Here we were just looking at the information for the first initial time, just to get a feel for what it was saying. And one thing I skipped over is part 2, the axis of symmetry. It's a vertical line, x equals a number h, which makes sense in our chapter on graphing, chapter 3. Vertical lines are always of the form x equals a number. That h carries over here by taking the opposite, and it carries over here into the axis of symmetry. So in our problem, the axis of symmetry is the line x equals 0. So here it is. We draw x equals 0. That's the axis of symmetry. It's called axis of symmetry because if you were to fold this paper after printing it out across this orange dotted line, both parts of the curve would just overlap on top of each other. That means curve sketching is not too bad. If you plot a vertex and then say a couple additional points, you can just mirror them across the axis of symmetry and get 2 more points essentially for free. So this is the quick way to graph these kinds of quadratics. If it's in vertex form, we pretty much are dealing with something like if it was in slope-intercept form, and we have all the information we need to start giving a really fast sketch. So that's exactly what we're going to practice on the next 3 problems. And then after that, we'll see what to do when it's not in vertex form. Those are probably the problems we're going to take a look at a week away from today. But any last questions at all, folks? Just looking at this initial information the first time? Okay, let's try it out all over again for some fresh problems. Example says, graph the parabola. This one's y equals x squared, making it another pretty good warm-up question. By plotting the vertex and 4 additional points, 2 on each side of the vertex. This seems like a lot when they say plot something with 4 points, but plotting with 2 on each side of the vertex is just reminding us that there is massive symmetry when it comes to every parabola. So we're going to use the axis of symmetry idea to kind of do 2 points to the right of vertex, and then just mirror them over to get the other 2 points for free. But notice it's, again, not strictly in vertex form. Vertex form means you have a particular h value, a particular k value. In a certain sense, it really is. It's just been simplified. So if you want to see how y equals x squared connects with the vertex form of the quadratic, you can take this and rewrite it as y equals, just like on the last problem, x minus 0 squared plus 0. That reveals the h in this problem is 0. The k in this problem is also 0. That means we know what the vertex is. Vertex is always the coordinates, h and k. And one particularly interesting thing always happens. We have a minus 0, which doesn't seem to cause much of a problem. But the next one is going to be a positive one, and we will take the opposite of this value, actually plug in a negative one. And if you look at the formula, there's a minus right here. Whether there's a minus or not, you always get the h value by doing one thing in particular, which we'll emphasize a lot just for practice. Take the opposite sign. Deserves an exclamation mark. That's an easy mistake to make on these. You're essentially plugging in a value, say right here, that's going to make this whole term 0. That's going to give your vertex. To make the whole x plus 1 term 0, you take a negative 1, the opposite of the positive 1 side, sign. This one's not as interesting because, well, it's just 0. Positive 0 and negative 0 are both 0 itself, so not as amazing. So we can say again right away on this problem, vertex equals 0, 0. Where following the color coding, it came from those specific portions. Or in other words, if you just looked at y equals x squared, it would have that same vertex, 0, 0 as well. And we can plot that vertex. The value 0, 0 would go right here. So that's our first point on the graph. We need 4 additional points. But one thing we can also do is make a prediction. The leading coefficient here is a positive 1 times x minus 0 squared. So our graph should be opening upwards. That's what should be happening on this one. To get the 2 additional points, we can just use the ordinary point plotting method. Pick an x value, then pick a y value. Y is determined by x because y is always equal to, I'll write the simpler version, x squared. And we already know if you plug in 0 here, you get 0 here for x, and 0 squared is still 0. So we want different values than the 0 here. But because of the power 2, these things grow fast. We want to pick something that's close to the vertex. Say a positive 1 would be close. Pick x as 1, feed it inside the function, and the y value is going to be 1 squared for a 1. So there's our second point on the graph. Pick an x equals 2, and the y value will be 2 squared for a 4. So go over 2, and we're already up to 3 and 4. So the growth rate is pretty fast on this. We wouldn't want to pick a 10 because we'd have to plot a height of 100 off the page now. Now we need 4 points, 2 on each side of the vertex. We have 2 on the right-hand side. But here's where the axis of symmetry, x equals h, helps us out. The axis of symmetry is x equals 0. Here it is. It overlaps the y-axis, x equals 0. And so I'll just use a dashed line to convey it's overlapping in that kind of way. But it tells us we can just reflect this point across to the left like that. If you plug in a -1, you should be getting a 1 as well. And that's not too hard to check. If you plug a -1 here, -1 squared is a positive 1. If you plug in a -2, -2 squared is a positive 4. But it should just mirror over from here to here. That's what this blue dotted line is trying to say. If you were to print this out, fold across the dotted line, these points all overlap, even the vertex, because it's right on the line. So we have 4 additional points, 2 on each side of the vertex. Last thing to do is a by hand sketch of this parabola. That was a terrible start. Let me try again. It should be kind of curvy down at the bottom and start growing fast. And it's not my best work, but you know, you're not meant to be an artist in this class. So if it looks about all right, if it conveys the right information, if I can tell it's opening upwards like on this one, and that it's somewhat rounded out in the bottom, you would get full credit on this one. When you go to sketch these by hand, really the only way you could lose points is if you drew something like, say, this. Parabolas don't do this at all. This looks more like an absolute value function, in fact. Parabolas start to grow faster and faster the further you get away from the vertex. So make sure you just kind of round it out a little bit like that to convey it. You don't have to put in the arrowheads. I just like to do that as a force of habit to remind me the graph didn't end, it's still going. And if it's a worse sketch than this, but similar in spirit, we're always using our imagination in mathematics anyways, you get full credit. If we did it in Desmos, here's what it would look like. X squared. And that's what the true shape should look like. By a hand sketch, that's not too bad. Well, that's our first one. We have about 4 or 5 more we're going to take a look at in these notes before we go to the next section. Any questions at all, folks, finishing this one? Okay, let's try this all out again. Because this is all still pretty new, let me take a screenshot of this so we can focus on all these ideas again on the next question. Let's push that to the next page. So same ideas, new function. This one's more built up, less of a warm-up problem. We have a leading coefficient as 1 again, so we're expecting the graph to open upward just like before. But the vertex is more interesting. It's at, let's say, for vertex V, we get the vertex by taking this number and this number along with the sign. And for the very first thing, as the note says, we always take the opposite sign. In fact, that doesn't even look right. It's a plus here, and it has a minus. But if you forced in a minus, it would have been minus a -1. And that's another way to rationalize it's always the opposite sign. So here, take opposite. But for the second half of the vertex formula, whatever is here, whether it's positive or minus, it directly copies in for the k value. So -3 would go here, and this is copy. So by the vertex form of this quadratic already, this is what implies the vertex would be. So let's plot that down. We're in the direction of -1 and then down 3. So this vertex is down here in quadrant 3 of the xy plane. We now need 2 more points, but really it's just the same kind of matter of let's get 2 points to the right of the vertex and then use the axis of symmetry, which is x equals -1, to get the remaining points. Since the axis of symmetry is such a helpful concept, let's plot it here. It would be optional in your sketch. Here's x equals -1, same as the h value. So now our table of points will be an x value and then a y which is equal to x plus 1 squared minus 3. And we don't want to go crazy and pick like a 5 value because again, these numbers grow really fast. We want to stay close to -1. What's close? Go 1 unit to the right. The best choice is 0. Or if you like negative numbers, the next best choice would have been -1, then pick a -2 next. So we'll pick a 0, this point, and then we'll pick a 1, this point here. Plug both of those values into the quadratic, x plus 1 squared. First one is nice. 0 plus 1 squared just gives us a 1 squared minus 3. That's just a 1 minus 3 for a -2. Then this plot tells us we're just plotting 0, -2. It would be right at that coordinates. Noticing it's going up. It should because we're told the parabola is going upwards since we have a positive quantity in front of the x plus 1 squared. Now do it again, plug a 1 inside here. We have a 1 plus 1 squared. So now it's a 2 squared minus 3. This is just a glorified 4 minus 3 for a value of 1. So when we're at 1, the height is 1, and that's our next point on the graph. So it gives us the entire, let me try again on that line, the entire right-hand side of the parabola. Here's about what it would look like as a freehand sketch. But it also gave you the other 2 coordinates. Guaranteed now, and you can check it as just an extra check in this problem, but it's guaranteed if you plug in a -1, so at this point, the height is going to be right at -2. And if you plug in a -2, you're now 2 units to the left, you're going to be at height 1, just like this point, which is 2 units to the right of the vertex. So at -2, you're at height 1. Now let's check this. If you put -2 right inside here, -2 plus 1 would give you a -1. But when you square that, you're going to get a positive 1. Hang on, let me think about this. Oh, I think I made a mistake. So this is -1. That value is -2. Let me fix these values here. I had trouble counting those coordinates. Let's put that mistake in something that shines a little bit better. So this point right here that I was looking at was -2. Let's check that out. If you plug -2 here, you get a -1 squared, which becomes a positive 1. -3 is -2. That's where my mind was breaking. And then that tells us you have this point for sure. At coordinates -2, -2. And then here's my other mistake. This one was at coordinate -3 for the x coordinate. So in the check, if you plug a -3 here, add 1 into -2 squared. -2 squared is 4. Minus the 3 gives us something at a height 1. So that 1 here does check out. So through symmetry, we get those points really fast. There's no harm if you cranked it out carefully, like on the points above. The axis of symmetry just gives you some options. You can do this in a really fast way if you chose to. Either case, we have the graph. This would be the full graph. If we plot this one on paper, here's what this one would look like. Not on paper, but rather on Desmos. Y equals x plus 1 squared minus 3. Notice how similar these two parabolas are. The one in blue is the new one. The one in red is just y equals x squared. So this negative 3 had a definite effect. It took a vertex that was here, right at 0, 0, and it moved it down a unit of 3 units. And the positive one, this is the weird thing, it didn't move it to the right. It goes the opposite direction. It moved it to the left. It moved left by 1 point. So those are the two parabolas in context. If we change these values, it's just moving it right or left by the opposite sign we see here. If we change values here, it's moving up and down by the same exact sign that you see right there. So we're just moving around the parabolas. The next one's a little bit different though. If you multiply something in front of the thing that's being x plus or minus a value squared, that's going to change the shape. It's either going to make it more narrower or steep, or it's going to make it more wider and more shallow in its growth rate. So that's our next part C we'll take a look into. So let's put this down below here. First, any last questions on finalizing this one? Okay, so next parabola. When you see something like this, let's go down through the order of thoughts that we should have when we take a look at it. A equals negative 2 coming from that leading coefficient. So that means this one's different than the other two. This one opens downwards. So a little bit different there. Also, we take a look at these values, the negative 3, positive 2, and this gives us a vertex. It's always a good reminder, so let's keep on putting this in the notes. Take the opposite here and put in positive 3. And on this one, directly copy. So positive 2 goes in, but now this vertex is the highest point on the graph, whereas the other vertex was the lowest point. That's just because this one's opening downwards. So if we go to plot with what we know so far, here's what the plot would look like. Go right 3, up 2. Here's the vertex, the highest point on the graph. It'll open downwards from there. And also, we have an axis of symmetry, x equals 3. The axis of symmetry will always go through the vertex, making the next part of the problem kind of faster to solve. We need 2 additional points, but the next nice points to put in would be 4 and a 5. So there's our values all written out. I think that's going to help me avoid mistakes like I made on the last question. So we need to find out the value of this parabola, this quadratic function at both 4 and 5, and then we can mirror them over for what the same values would be for both the 1 and the 2. So here's our next point plotting method chart. Here's x and y, but y equals this time negative 2 times x minus 3 squared plus 2. We'll check the value for y when x is 4 and when it's 5. Then we'll mirror those values for when it's 1 and a 2. So starting off, when x is 4, we're going to get negative 2 times. Inside the group, it's 4 minus 1 squared. So that's a positive 1 squared plus 2. But this reduces to just negative 2 plus 2, giving us a 0. That makes sense. That means it's opening downwards. It goes down. It intercepts the x-axis here, so we get an x-intercept on this one. But that means that also from this point moves down here and produces a 0 as well when x is 2. So that's our axis of symmetry in action. We can just get that point immediately for free once we found this one. Then do it again. Plug in a 5 into this quadratic function, and we'll get negative 2. Inside the group, it's 5 minus 3 squared, so 2 squared, plus 2. This is -2 times 4, so -8 plus 2 for a value of -6. So that dropped really fast, but that's just because this factor of -2 is making it a really steep parabola. So -6, 1, 2, 3, 4, 5, 6. We're way down here when x is 5, so it's dropping really rapidly. But if when x is 1, it's also dropping by the same rate, you'd also be at -6. So we get -6 at 1 at the same time, and then the whole sketch would look about like this. Feels like I'm doing a little bit better with more practice, but still isn't perfect. It doesn't need to be. That's our quick sketch of this graph. So this is the vertex here. And again, it's interesting because this one led to a maximum point, an overall global maximum to this function. So if this came from some kind of word problem, maybe we're maximizing time, distance, area, speed, we know that the problem would have an overall maximum, just like in the problem that we're looking at in section 9.5, just to tie into what we did before. In this application over here, we were looking at the height of arrow being shot up. If we find the vertex of this thing, we'll know the maximum height it achieved. It's opening downwards because the leading coefficient is negative, but getting the vertex of this is not as straightforward because this one is not in quadratic form, vertex form, and we can't easily put it in vertex form like the others because of the variable t right here. So there's more to do with those kinds of equations, but that's the purpose of the so-called vertex formula that's coming up next. This one is going to allow us to take a problem like we saw in section 9.5, this equation right here, find the vertex of this, and then once we find the coordinates of that vertex, we'll know the maximum height the arrow ever achieved, and even the time t when it happened. So that's the idea to tie in with why we care about these parabola shapes out of nowhere. Parabola shapes are pretty natural in certain things in physics and other optimization problems that we're going to take a look into. And the vertex formula is just the next key that's going to allow us to compute the vertex of these trickier problems down below. I don't think we can do it in 2 minutes though, so this will be our stopping point for the day. Any last questions at all before we call it a night? Okay, well, have a good one. If any questions come up as you're studying the exam material, I'll be available by email. Don't hesitate to reach out. Have a good one, and I'll see you later.